9. Hi everyone, we are a team of 3 people, myself Kavita Yograj, Pradeep Kumar and Mayank Shah. We are going to talk about methods for parameter reductions in deep CNN models. So when we say methods for parameter reduction, there could be a number of methods. Here we are concentrating on distilling the knowledge and using enhanced architecture, mobile net architecture, and then finding layer-wise differential network architecture using heterogeneity and hypothesis. So I will be presenting on distilling the knowledge in neural network. So what is distillation? Distillation is basically any machine learning model can be trained on the same data. A number of models can be done. So these a number of models, model 1 can grab some data, some insights that model 2 hasn't, and then ensemble of models might actually be good in model, the throughout model, right? So, but the problem with this is it's cumbersome and it's computationally very expensive to, if it is individual models are larger neural networks. So basically, Caruana and his collaborators try to address this problem of deploying this computationally expensive model into one easier model. But the problem still is cumbersome model has not been addressed. So this distillation process in this particular paper is addressing this using specialist models by capturing the fine-grained classes and using one or more full models also. So let's see what is this distillation process. Distillation process is architecture agnostic and it's used for generalization, and it's there to actually consolidate all the knowledge of the main model into a submodel. So what is this distillation? The pre-trained neural network is actually there, which is a larger neural network. You can see the teacher model there, and the output that you see is the soft labels or soft targets. The knowledge from that is distilled to a smaller module called a student module, and student module is now, as you see, are lesser in terms of size. So it's and we are getting the same state of the accuracy as you see below. The teacher model's knowledge is now transferred to student model's knowledge using the transfer set data, and the teacher model has the same accuracy as the student model, you can see. So even though it's of small size, so we are achieving the state of the art accuracy with the fractions of size of neural network, and the response time is also much smaller. This way, we are able to achieve the same thing what larger neural network was able to achieve. By the way, we said it's architecture agnostic. With that, we are able to run it in single GPU or with CPUs also. So the generalization ability of this model is something. So generalization ability of a model is something that we need to, why it is moving? So the generalization ability of this model is something that we need to get to know how and what they're doing here. So the main objective of generalization is to generate good results for the test data and whatever the test data it could be. So problem with ensemble models is it has very little influence on the cross entropy, and the probability are so close to 0. So Caruana and his collaborators, we are referring this paper a whole lot here. So Caruana and his collaborators have achieved this without using probabilities, rather using the logits. Logits of the probabilities produced by the softmax function for the particular targets, basically. And also they calculated the square difference between the logits of a cumbersome model and the logits produced by a smaller model. So with this paper actually trying to come up with a generalized solution called distillation process using the temperature setting of a cumbersome model and the smaller model. And they also use some matching logits. So let's see this little caricature we have done here. It's high temperature. We are training on the transfer set for each of the case of a cumbersome model. When we say cumbersome model, we have many ensemble models, right? So each of these ensemble models has some transfer set of data. For each of those cases, we are actually training on the transfer set. We are recording the high temperatures on each of its softmax and use the same high temperature on our distilled model. So now we have a specialist model with the same temperature that it was working for the larger model. So T in this equation Qi, you see T is a temperature which is normally set to 1 using a higher probability distribution, and Zi is the logits for Zi model, Zj is the logit for Zj model. So what are the distillation process? What is the objective of a distillation as we see now? So cross entropy with soft targets is the number one objective, with higher temperature that we have to calculate for the soft max, which was same as the cumbersome model. So each distilled model should be having the same higher temperature as the cumbersome model. So that's the objective here, first objective. Second one is to get the correct labels of the soft max, so that we don't miss on the correct labels. So it has to be correct labels, and the temperature setting needs to be 1. But observation of this paper tells us that the second objective could be given lower weight than the first objective. Well, let's see what the actual examples talk about. So magic, we are talking about logits a lot now, right? So let's see, what is this matching logits? Matching logits is a special case of distillation actually. So at higher temperature, distillation is equivalent to the minimizing Zi and Vi. So here Zi is our is our soft small model. So the zero means separately for each transfer case is what we got, the differentiation of that at high temperature. At lower temperature, the distillation did not even play any big role. So I mean, it did not give much attention for the matching logits at all. And then but they might be advantageous, they might be carrying some information, is what the assumption is. And then the experimentation results showed us that. The takeaway of this is, if the distilled model is too small to capture all of the knowledge, then can we use the intermediate temperature? This is the strong suggestion that let's ignore the negative logits. Let's take the intermediate temperature. Maybe that would work best. So they conducted experiments on 3 different data set here. One is on MinSet. The second example is on JFT data set. And the third one is on speech recognition data set. Here, it was 1,200 hidden units, 2 hidden layers and 1,200 hidden units. They were able to reduce that large network into 300 units with distilled nets, which is really good, isn't it? 1,200 to 300 units we came down to, and it's same 2 hidden layers we have, but the temperature setting was 8 here. And with temperature settings in the lower or medium range, 2.5 to 4, 2.5 to 4 work significantly better than higher or lower temperature, is what their temperature experimentation on. And they used only 30 units. It's really good that this particular MinSet data performed remarkably well. And it also performed remarkably well even when the data was not even seen before. So which is really good. For example, number 8 or number 3 was not even seen in the MinSet data set, but it was able to classify that particular data has 3 and 8 in the small distilled model. Let's talk about another experiment, which is on speech recognition results. They had a baseline model which got the test accuracy of 58.9, and the WER error has 10.9%. And they also built 10 separate models and ensembled them to 61.1%, which actually resulted them with 10.7% WER. Whereas their distilled model performed same as their ensemble model with just 0.3% down. So experiment on speech recognition actually showed them that with different temperature settings and cross entropy on a hard target, they were able to achieve the same accuracy, but WER was not reduced because of the mismatch on the objective function. So now let's talk about another data set that is on, I'm not able to move. Okay. So now let's talk about the JFT dataset result. The JFT dataset took about 6 months to do the deep neural network training from Google for the baseline model. Here in this paper, they built a specialist model by clustering them into different classes. So you see this assigning classes to specialist. These are many smaller clusters, and on each of these clusters, they trained the special models. And there were some classes which were not really adding any value. In that case, they actually put them in as a single dustbin class, and they actually had one generalist model and many specialist model. With that, they were able to achieve much faster results. And number of classes, actually they reduced number of classes to using the clusters here. So overall, in conclusion, what we want to say about distillation process is, with 61 specialist model and a baseline model on the JFT dataset, they were able to achieve better accuracy, which is 26.1 as opposed to 25%. So they were able to achieve 1.1% accuracy better, and distillation works very well for transferring knowledge from an ensemble model or from a highly congested regularized model into a smaller distilled model is what we have learned in this paper. And in MinSet dataset, we learned it performs remarkably well. With speech recognition, we learned with a large NN neural network, we were able to condense it to smaller single NN. With JFT dataset, we saw the performance improvement. So with this, distillation process is one of the method to improve the performance and parameter reduction of neural network. Thank you, by the way. I'm going to pass it to Pradeep.
Sorry, Mayank.
Mayank.
And I'll be talking about parameter reduction using convolutions, and basically we'll be using depthwise convolutions. Now, when we talk of parameter reduction, whenever we talk of parameter reduction, what is the parameter? In terms of neural networks, we are having input there, then certain weights and addition of those weights, multiplied additions of those weights, and then the hidden layer will give us output, and that will be taken to the output layer. Now the parameters are basically the weights that we are taking in the edges that are taking throughout the network. Now when we go for the parameter reduction, what we're trying to do is we're trying to optimize the number of weights that we are taking. Now the number of weights, as we see, if we induce more layers into the network, then the number of parameters or the number of weights will increase also. So there is a limit to how much the number of weights can be assembled or can be associated in a specific neural network. Now, why we need parameter reduction is basically because if we keep on increasing the number of weights, or if we keep on increasing the size of the neural network, then it might not be very feasible for us to implement these neural networks in terms of practical situations or in terms of embedded systems or mobile systems as well. So that is why where the hardware is not that much powerful and where we have hardware dependency, we need to control the parameters so that we can efficiently work in the learning modules as also. So there are multiple advantages of parameter reduction. Those are improved accuracy along with reduced size. Now it was initially considered as a myth that if we reduce the size of the neural network, the accuracy will drop. With the simulation and with the lot of models that have come into the picture in last 5 years, it has been accepted that even we can increase the accuracy of the model even with the reduced size, and parameter reduction models have proven so. Now there are lesser number of layers, which means that there is always a lesser computation time that is coming into the picture. So that makes the machine learn more faster, and the accuracy also improves over the time. Now it also deals with, because parameter reduction will also actually give us very less overfitting, because as the number of layers increases, the component or the exponent in the graph will also increase. So that will lead to somehow, the problem of overfitting. So if we minimize or if we optimize the layers or number of layers, then we can solve the problem of overfitting during training also. So, and plus these all can be deployed in embedded systems and memory constrained CPUs also. So now when we talk of efficient models in terms of CNN, there have been multiple models that have been that have already been launched, like Efficient Net, Efficient Det, Mobile Net, Exception, Squeeze Net, Mobile Net version 2, Shuffle Net, and Thin Mobile Net. Many of these efficient models actually work on the concept of depthwise convolution. So we'll be talking about some models which are working on depthwise convolution, but before that we'll be talking about the basic background topic that is being used in all of these models, as is batch normalization. Now, why do we require batch normalization, and what really is batch normalization? Now, as the term normalization itself suggests, normalization is normalizing the inputs or normalizing the parameters to a certain limit. That is, if suppose we have a varied range, we can have range from 1 to thousands to lakhs and everything. But when we try to portray it in terms of digital scenarios, we need to put that range into a specific computer readable form. So we define a discourse in which we are going to represent all the data that we have within this discourse. So suppose if I have a discourse of 0 to 1, now all the parameters will be defined in this discourse of 0 to 1, that is normalization. Now we can do the input normalization, and that is the primary aspect, or that is how the primary we start with the learning modules, that when we first step is to normalize the inputs. Now what happens, we have normalized the inputs, but when we go through the model, there is a specific weight which is far more than all the other weights combined together. So if you consider a scenario, this weight will overtake the proceedings of the neural network, and the weight will be an advanced weight, and all the neural network would be controlled by this specific weight structure and the activation function following this weight structure. So that is why to reduce or to contain this type of scenario, we introduce batch normalization. Now what batch normalization does is, batch normalization also normalizes the activation functions in the layers. That is, even though the weight of a specific given network is high, but once it goes to the activation function, the normalization will keep it in a specific range. That is, for instance, let's say 0 to 1. So the effect of that specific weight will narrow down, and we will not be having an unbalanced network. So this will balance the network. Once the activation functions are balanced, the speed up of the network will automatically be there, because the all the topics or all the weights or all the information that is being transferred to the next layer is also normalized. So batch normalization is one such setup to normalize the activation functions in order to make the learning process more faster. So whenever we talk of models, there is always a procedure of we need normalization. So we use batch normalization, and we use convolutions and the activation functions apart from it. So in all the models that we have discussed, that we will discuss, there will be three things. Number one, there will be convolutions. Number two, there will be batch normalization, and then number three will be the activation functions that we will be using. So apart from this batch normalization, now let's come to the concept of depthwise convolution. Now the first image that you can see here, this is a normal convolution that takes place. That is, if suppose we have an image of this type, that is, it has an XY coordinate and it also has a depth coordinate, that is the number. If suppose we can say that these are the coordinates. So in a normal picture, if you consider RGB, your image would be some X into Y into 3. Here you have multiple number of depth, or here you have multiple pixels in terms of depth or multiple colors. So this is a complete picture that you have been given. Now if we select a specific frame, that this frame is taken as the reference frame, and this frame will now be convoluting frame will now be going through all these models and will be then giving you the outputs in a single value, that will be the convolutions. This is how a single convolution or a normal convolution actually works. What happens in a depthwise convolution is, depthwise convolution basically takes away the depth of the setup. That is, one convolution will be taken for every single depth that is there. So if there are m elements, or if the depth of this picture is m, there would be taken m different frames, and these m different frames would be having different frame. These m frames would be having some small frame also, this buffer frame also, and now then they will convolute together, and finally they will give us a specific combined unit. So if we talk into it, what is the use of depthwise convolution? The depthwise convolution will actually make the transition more faster, because if you look at it, the number of observations being done here would be much more higher than number of observations being done here, or number of calculations being done here, because here for every single element, if we take this element, we will be having 9 into k, the depth elements. So that will be the number of computations we will be having. Here the automatically, if we have one layer, so the depth layer would be 1 and convolution layer would be 1 into k, and if we add on to it, then also it will be far lesser than this. So that's why depthwise layer convolution actually makes a bit of faster. But then there are also separable convolutions. Now separable convolutions are of two types. One is spatial separable convolution, and another is depthwise separable convolution. Separable convolution, as you can see here, this is a normal convolution that is there, that is an image, and this is the frame that we are taking. Now if we say this is a 3 cross 3 frame, so there are 9 elements in this. These 9 elements will be taken through all these images continuously, and for a single frame to be convoluted, we'll have 9 operations to take care of. Okay? Whereas if we change this 9 cross 3 matrix, 3 cross 3 matrix into 2 matrices of one of 3 cross 1 and another of 1 cross 3, or we divide these matrix into 2 separable spatial matrices, then we would be able to actually get, in here we'll be having, first we'll having 3 multiplications, or we'll be having 3 operations, and then again here we'll be having 3 operations. So in total we will be having only 6 operations, which is a gain of 3 operations on a simple convolution. So this is a spatial separable convolution that we can use for parameter reduction. But there is a disadvantage to it, or a difficulty to use this. That is, we would not know, or all the matrices would not be dissolved in in 2 different matrices. Like every single 3 cross 3 matrix cannot be divided into 2 matrices of 3 cross 1 and 1 cross 3. So this model is not applicable in day-to-day lives, or this model is not applicable to every single scenario that is there. So that is why there is an enhancement of it that is called depthwise separable convolution. Now what this depthwise separable convolution does is, this depthwise separable convolution takes 2 convolution methods. So instead of going for 2 different spatial convolutions, we are going for, first we go for a depthwise convolution. That is, we take the n dimensions or the depth of the scenario, and we take the depth and we take the number of frames that are in the depth. We take them along and we convolute, and we make a depthwise convolution as we studied earlier. Then we go take them through to a 1 cross 1 convolution. This 1 cross 1 convolution, what it will do is, it will actually take them together and it will merge them into a 1. So if we have a 512, 512 and 12 frame, this can easily be convoluted to 512, 512 cross 1 frame using this depthwise separable convolution. Now, because we are using depthwise separable convolution like this, so depthwise convolution will give us a 12 cross 5 frame, and then 1 cross 1 convolution will give us a 12 cross 1 frame, ultimately leading to a parameter reduction. That is our main goal. So this depthwise convolutions has been used in multiple technologies. Number first, that is our mobile net. So now mobile net is one of the most basic, or one of the foremost models that came using parameter reduction. So mobile net actually was implemented to work on AlexNet, and it efficiently reduced the work of it efficiently reduced the parameters on AlexNet by multiple times. So what mobile net actually does is, it takes a 3 cross 3 depthwise convolution. So this depthwise separable convolution is, first it is a depthwise convolution. This depthwise convolution will then be taken to your batch normalization. This batch normalization then will be taken to a ReLU function, that is your activation function, and will give you a specific. So we, after this depthwise convolution and using the batchwise, you will be getting this type of frame where you are having actually the dimensions of the input image and the dimension of the intermediate image are almost the same. Then the 1 cross 1 convolution will take place, and this 1 cross 1 convolution taking place will actually give you a singular picture or a reduced parameter out of the scenario. So once this convolution takes place, then again branch normalization is done, and this is again taken to a ReLU function, making it a much more induced setup for working. Now when you go for mobile net will actually be taking about 13 layers of such scenarios. So this is one layer that has been taken care of. Now similarly, about 13 times this layer will work, and finally we will be getting an out plus class on basis of a softmax function as a classifier here. So this is how a mobile net actually works upon with the function of the depthwise separable convolutions. Now after the mobile net, there is again a model called exception. Now this exception also uses two convolutions, that is the pointwise convolution and depthwise convolution, such as mobile network does, but it uses in a reversible manner. A reversible manner means, first of all, it uses a pointwise convolution and takes an intermediate image out of the initial convolutions that we have. Now these convolutions that we have, or these intermediate image, now will take into a depthwise convolution and then integrate it together in order to make the final parameter change that is to be there. So this is the exception model that came into the light. There is a performance gain of exception also. This is also a performance gain on AlexNet, and the parameter reduction is substantial. Now this is the basic fundamental that what it takes is, so input is given. Now 1x1 convolution it takes. So 1x1 convolution will actually make a concise, or we can say we will reduce the parameters here, and then the 3x3 convolutions will expand it, and then it will generate features out of it. So again, the parameters would be more than what we expected, but still it will be lesser than the normal convolutions that are there. So there is an inception hypothesis regarding this also. A convolution layer attempts to learn filters in a 3D space with 2D space with two spatial dimensions, that is height and width, and a channel dimension. Thus, a single convolution kernel is tasked with simultaneously mapping cross-channel correlations and spatial corrections. So basically, a single channel convolution, that is this 1x1 convolution, will actually map the cross-channel correlations further in this scenario. So this is also substantially able to minimize the parameters and improve the accuracy on AlexNet. SqueezeNet is one of this then again a parameter reduction technique where it uses the concept of squeeze and expand. So this squeeze and expand, or this entire setup together, is called as a fire setup. So what happens is, in the initialization, in the input layer, it takes as input the image or whatever the image size is. Then it takes us to the primary convolution, and after the primary convolution, it takes us to the 8th round of fire. Now 8th round of firebox is basically, it takes first 1x1 convolution is there, then this again 1x1 convolution is transferred into 3x3 convolutions, just like we did in exception. But instead of having only one round, it takes it to the 8th round, and it uses batch normalization and ReLU as in between, and finally we get the output in terms of the reduced parameters also. Now MobileNet V2 is an advancement on MobileNet, and it works on the function of bottlenecks. Now what bottleneck is, suppose we have an image of 56.56 cross 24. Now this 24 is the depth of the image. Now if we take the depth of the image and we take depthwise convolution, so every single frame, that is 55, we will be having 24 frames of 56 cross 56, and all these 24 frames can together be taken as one instance of the data itself, which would be primarily functioning. Now this 56 cross 8 data, that is called as a linear bottleneck, is then transferred or then probed into multiple depthwise convolutions in between. So the line-wise solution would be that it will be first taken into an expansion convolution, that is 24 is being factored into 6, or a total of 144 depth frames are being created. Now depthwise convolution will again make this 144, and then when we go for the point-wise convolution, it will again marginalize it to 56 cross 24. Now we have also the initial bottleneck, that was a 56 cross 24, that is taken as a residual correction, and then the losses are contained and the losses are calculated, and somehow the output is to be generated, and the output reduces the parameters. Now when we talk of the input and the output layer, almost the function size is same. You can take it as this selection. So H cross W cross K is your input size of the image. Now if it is taken to the 1x1 convolution, it gives us an image of H cross W cross TK, that is the number of elements, that is if there are 24, so 24 times into K will be the output that you'll get. Now this, it will be turning as an input for this 3x3 convolution network with a ReLU 6 function. Now when we go through this, the 6, because we are having a 3x3 multiplier, we will be having the size of H by 6, H by S into W by S into TK. So the depth will remain the same, that is TK. And then again, if we take it to a linear 1x1 convolution, we will be having H by S into W by S into K dash. This would be quite similar to H cross W cross K, depending on the parameters that we have taken. So mobile net is also will actually go with 32 filters followed by 19 residual bottlenecks. So 32 filters means that we are having these many filters, or we are taking 3 cross 3 and 1 cross 1 frames. These 3 cross 3 and 1 cross 1 frames are called as filters. We will be having 32 filters followed by 19 residual blocks. 19 residual block means that if one block, so this is one residual block, and such 19 residual blocks are there in this mobile net, which actually imposes parameter reduction in a very profound manner. Now finally, we have a thin mobile net setup. This thin mobile net setup is also an advancement on mobile net and mobile net v2, where instead of having a depth separable convolution, it takes separable convolutions. Now what is the difference between depth separable, depthwise convolution and separable convolution? Now when we talk of a depthwise separable convolution, it will first have a depthwise convolution, then it will take a pointwise convolution, and finally we'll be having the function out of it. But here in separable convolution in thin mobile net, the depthwise convolution and pointwise convolution have been combined together in a single frame, and that will give us a separable convolution layer. So now there are multiple such separable convolution layers, which goes through the concept of batch normalization again and go for drop activation. Now what drop activation does is, if you can see this slide, here is the normal activation function of ReLU. So this will actually give us an input and provide a non-linearity to it. But if we use a drop activation would actually induce some randomness into the setup. That is, in some instances, the ReLU function will take over, and in certain functions, the ReLU function will not take over, but linearly the data will be forwarded outside. So there is a probability associated with. So if we are having a probability of P, that is out of a given set of times, with probability P, the ReLU function is being firing, then there will always be a probability 1 minus P where the ReLU function is not fired and the randomness is generated into the setup. So this randomness and the separable convolutions put in together gives us a very well defined parameter reduction with with a very good accuracy as well. So if we talk about the comparison and all in amongst all these modules, we can see that LXNet being the most the oldest neural network out of it, is having about 60 million parameters. But once we go for a mobile net will actually reduce the parameter to 1.32, and even the accuracy on the ImageNet database is rising from 57.2 to 60.2. And similarly, if we then go for SqueezeNet on the same ImageNet dataset is going to give us a parameter reduction of 1.25. That is, instead of having 60 million or 1.32 million parameters, we are having a 1.25 million parameters. But the ImageNet accuracy is still better than LXNet, but not better than MobileNet. Now, if we go for thin mobile net, the accuracy of thin mobile net is 85.61% or ImageNet dataset, and the number of parameters is like here it is 60 million, here it is 1.32 million, here it is only 814,000 parameters that are available for working in thin mobile net. And finally, in mobile net v2 on the same ImageNet dataset, there are 3.4 million parameters, more than MobileNet and SqueezeNet, but still the accuracy is there, but the CPU timing is computationally less in MobileNet v2. So this is a basic conclusion, or this is the basic comparative study about all these model parameters. There are many more model parameters that are available, which are not of depthwise, but there are still parameters which can be used for parameter reduction. Now, as per the references, these are some 5 reference papers which we have tried to study. We have studied more papers, but because of the papers not being of depthwise convolution, we have not included them in the scenario. Thank you. Now over to Pradeep.
Thanks, Meg, for such extensive presentation on MobileNet. I will try to wrap up my stuff, and I'm going to present the third paper, which is a heterogeneity hypothesis and finding layer-wise differentiated network architectures. So the organization of my presentation would be like, I will introduce the topic, and then I will mostly focus on the 3 key issues that authors have addressed, and then I will just briefly mention the takeaways of this paper. Sorry. So actually, with the advancement of the deep learning, the manual feature task has been overtaken by the convolution neural network. And because of this, the neural network architecture has taken the center stage in this area, basically. So there are several directions of the designing neural network architecture. One is the manual design, and like we know, the VGZ or residual based network like Resonate or UNIT has been manually designed. There are other different direction which is very important is a network neural architecture search, and we have NASNet and PNAS. So we have the third direction which this paper is mostly focusing on. It's not based on the overall architecture design, but it's based on the architecture optimization. And we can see that this paper is mainly proposing a cost-free fine-grained architecture optimization, and it tried to adjust the number of channels for the layers of already existing network. But there are certain assumptions which this paper have like before starting this work. That is, the layer-wise adjustment can lead to redistribution of the computation and also improve the performance for a predefined network. So I will briefly talk about the two work which has inspired basically this current research. One is the lottery ticket hypothesis, and this believes that there exists always a sparse subnetwork for a predefined network for which can outperform the original or baseline network for a given number of iterations. But this work has certain limitation. It works for the selected weight and it randomly drops the weight, and it creates the problem for the trainability of model. So when you go for a back propagation, this creates some discontinuity, and the back propagation is a problem for this kind of thing. Also, there's a problem with the explainability. So you cannot trace back where from this benefit model is getting or the improvement of the performance is coming from. So current work that addresses this problem, and it can trace back which step is benefiting or improving or boosting the performance of the model. Second is the channel pruning. Basically, it's a structured, not unstructured channel pruning, and it's very important that for this work. And as Mayank extensively talked about this mobile net, so I will keep it brief. And we can see here that the prune network can outperform the original network. Here we have a various width parameter. Alpha shows the width parameter which can go from 0 to 1, and we can see for under one width parameter, it's always possible to get an improved model, and here it's visible. Like we can see this error rate is smaller for the same alpha parameter, which is 0.3. But there again, there is some constraint for this. It's only applicable for the small data set, and there is a problem of a generalizability of this problem. It cannot be enhanced to the larger data set. So the three key problems which I said at the beginning, I will discuss those things. The first is to investigate the existence of LWDNA that can outperform the original architecture, and the heterogeneity hypothesis comes for a rescue, and it highlights the three key points. One is the same training protocol, which provides the fair comparison between the baseline and optimized networks. And second, it only adjusts the number of channels in a given layer. So it doesn't grow or decrease the number of layers, but it only plays with the number of channels. Second is that optimized network as compared to the baseline network has lower level of complexity in terms of both parameters and the computation. And if you see the figure number 1 here at the top, we have two. One is the baseline network for the ResNet, and other is the ResNet 4GF. And we can see always the complexity for this LWDNA model is less. In terms of performance, we can also see in this table the LWDNA always performs better than the baseline model. And then second key problem is how to find this LWDNA model in more efficient manner. So first thing it does, it starts with a baseline model. And then the main goal of this is to cost-free architecture optimization technique. Cost-free provides a fair comparison between baseline and the optimized network. And in this paper, the author uses the single shot networks shrinkage method to find this optimized model. So first they initialize the network, then they prune this, like reduce the number of weights in the initialized network, and then they train the prune network right from the beginning. But with this approach, there are two problems. One is that they cannot grow the layer, and then second one is unstructured pruning. Next, we will see how they solve these two problems. So to solve this problem of uh, like they cannot grow the number of layers, they propose a vector called C, which is a configuration vector. Here we can see this is a C, the configuration vector in the configuration space. E here denotes the configuration space, and it is L dimensional vector. And L dimensional vector simply means this network has L layers, and each vector corresponds to one layer. And then this configuration vector is expanded, and the whole idea of expansion is to increase the solution space where you can go and find better solution for this configuration vector, because this configuration vector C is initialized manually and is not always optimal. So idea is to come up with the optimal configuration vector which can reduce the complexity of the model. And the second problem is the unstructured or unconstrained pruning. So the whole idea is solved by the reparameterization of the network, and which is solved by the hyper network. So hyper network, what it does, basically we have a backbone network which extracts the features from a neural network, and this extracted feature is given to attached to a latent vector, and this latent vector is given back to the hyper network, which creates new weight, and this weight is again fed back to the backbone network. And that's the whole idea behind this reparameterization, like creating a new weight using the hyper network. So here we can see this is initialized with a single pruned element of a vector. The whole vector is not pruned. That's the key element from this. And then this leads to the pruning of the whole vector. And the whole pipeline can be summarized here. First, they widen the baseline network, then they use the hyper network to reparameterize and conduct single shortest shrinkage. It has two components. First is to compute the gradient with just one random mini batch. And that makes it cost free because you are using only the single batch, and then greedily shrink the network with respect to the gradient, and finally just train the LWDNA model with the same training protocol, because it also keeps a fair method to compare it with the baseline model. The second is the explainability, which we discussed in the beginning, that the other model has this problem. So this model is also explainable here, and it proves that the CNN had some redundancy, and it is possible always to find a layer-wise specific general kind of a configuration that is comparable with the baseline. And also reduces the lower the model complexity, and then also it redistributes the computation throughout the model. The two evidences that we can see here is for the ImageNet and for the tiny image set data, we have always higher accuracy for LWDA model, and there's a lower error rate here. And in this case, we can also see that it has a less overfitting. That is, the training accuracy is also reduced, but test accuracy goes up. So this achieves like higher, lower overfitting in the model. And the key three takeaways from this study is that it empirically establishes that the proposed heterogeneity hypothesis, that it is always possible to also identify a LWDNA model for a predefined model. And it also establishes that it's possible to get a cost-free fine-grained architecture optimization for a given network, and there's no computational overhead because it only uses the single batch. And it's also possible to improve the network performance, and it can be explained where from this benefit model is getting. Thanks.